the agenda for comparing two binomial parameters, and we're going to be in the unequal ends, or unequal sample sizes per group. We're going to set up the hypothesis, look at the distribution of the test statistic under the null and alternative, and then we'll illustrate this within R. The data, sample 1 comes from a binomial N1, P1. Notice the sample size is N1. Population 2 comes from a binomial N2, P2. We want to test whether the two population proportions are equal or are they not. And then our test statistic is this, the difference of our P1, P2 estimates divided by a variance. Under the null hypothesis that the population variance or proportions are equal, then we can those will be the same, and we can pull it out of the sum. And so this is the test statistic under the null. So when calculating sample size, here's our N1 and N2, and for our estimates here for population proportions, when calculating sample size and power, we pick values of interest P1 and P2, and under the null that they're the same, we average the two that we pick to find a common estimate. And this is the approach that a lot of people take, and it's the approach that R takes. So quickly, that under the null, this distribution is a normal 0-1 random variable. So you can also, and where the P here, notice there's no subscript, is we're just going to average the two values that we pick, P1 and P2, to find this. In R, we're going to plot P1, P2 values across the x-axis, and it's going to be normal with a mean 0 and this standard deviation, and you'll see that in a second. Under the alternative hypothesis, our test statistic follows a normal with this mean and standard deviation, and this here is what shifts the distribution over the rejection region. Is when you increase n, this denominator gets smaller, which then makes this value bigger. So it shifts it more and more. So increasing sample size keeps shifting this distribution over the alternative region, which increases power. But since we're in the unequal sample size case, we need some more structure about our sample size. And what we've done in the past videos is we let the sample size from first population be K1 times N, second is K2 times N, where N goes from 1 to infinity. And when we set it up like this, we can have 1 to 2 randomization ratios, 5 to 7, 1 to 3, and we just need a little more structure. We can't increase these n's the same by 1 each time, because that's the equal sample size case, and we did a video on that. Well, let me illustrate this in R. Okay, we're in R. I'm on a Ubuntu Linux machine, and we're going to illustrate two sample binomial test with unequal ends per group. We're going to test the null is that the proportions are equal, alternative is they're not equal. Let's pick some numbers to illustrate this. We're going to just pick 25 and 35 for sample sizes. Let's pick some values in the alternative region as 0.5 and 0.3, and we'll store those in P1 and P2. We set up our Q, which is 1 minus P, and this estimate here is our estimate of P under the null, where they're equal. So you just take the average of the two values that we picked in the alternative region. And now I'm going to illustrate this with a graph, and then we'll run the computer program to calculate power. And I'm going to do that. I'm going to create two plots on one page, and you do that with the MF row or MF column options. And I pick 2 and 1 for 2 rows, 1 column. I'm going to create some data to plot. And so this is the P minus P1 minus P2 values. So this is the null distribution. We're assuming that the proportions are equal. And then we'll shade the rejection region. Here it's a two-tailed test. So we have rejection regions on both sides. Now let's draw the distribution of the test statistic in under the alternative hypothesis, and this is this, and it's a shifted normal. And so power would be the area under this curve in the rejection region. So there's going to be two little areas here. I'll shade those green, and you probably can't see that little thin green line here, but that's it. So this is how you calculate power. And we're going to use the D norm and P norm and Q norm functions, which deal with this normal density. But in the books, everything is transformed to a Z. So you often don't see it like this. So they take this normal curve here and transform it into the standard normal curve. So that's what this black line represents. Then they create shaded regions here. And matter of fact, these shaded regions here, the rejection regions, are from this curve. And then you often back map it or transform it back to here. And so now this normal curve can be transformed into the standard normal. So this green area, remember there's two little regions here, that represents this in the shaded or in the standard normal curve. So this green area is here, and then this green area is this little tiny sliver here, which you probably can't see. But usually power is written in terms of the standard normal curve, and you always kind of wonder where it comes from, but it's being mapped from two other curves. So now let's calculate power. So the R stands for the right, and then there'll be an L in a second, which stands for the left tail. So to calculate the right tail, we want it from this cut point. P norm is the cumulative distribution function, and so that's that. And the left curve is done the same, and we add them, the right tail and the left tail. So we have a power of 34%, and that's with a sample size of 25 and 35. Now to find power, remember we have to create some structure. And so I'm going to have a K1 of 1 and a K2 of 2. So that allows us to have a 1 to 2 randomization. And then I'm going to set up N1 and N2 to be those constants times another variable that we're going to increment one at a time. So I'll just set it equal to 10. So now notice that we have sample sizes of 10 and 20. And let's calculate power to see if we're in the range. It's only 18%. So we want to increment this in by 1, recalculate, see if it were 80% or more. If not, then we recalculate. But we're going to let the computer do that. We're going to create a little while loop. And then while our power, their estimated power, is less than 0.8, keep doing it. So we're going to increment it by 1 each time. And then when it stops, we've reached the right power. So here we need a sample size of 71 and 142 to achieve an 80% power, comparing these two binomial parameters. So anyway, hope you enjoyed the video.